All right, so hello guys, and welcome back to CS25. Today, I'm very glad to welcome Victoria Lin from Thinking Machines Lab. So she's a member of technical staff there, where she focuses on native multimodal intelligence. And she is passionate about building AI systems that empower humans to tackle complex, knowledge-intensive problems effectively. And previously, she was a research scientist at Meta AI and Salesforce AI Research. And she received her PhD from the University of Washington. And without further ado, let's give it up for Victoria.
Thank you for having me. So can people hear me okay? So I'm very glad to be here today and talk about native multimodal language models. So a declaration is this talk is going to be exclusively focused on public materials, and the talk represents my own opinion, not of my employer. So without further ado, let's start it. So I think without much argument, large language models is one of the most exciting breakthroughs happened in the past few years. I think nowadays, probably like everyone sitting in this room will use language models a little bit, like during your daily life. So for example, like asking questions to ChatGPT, using like Cloud Code or Codex to help you to code your project. So these models were built based on next token prediction over symbolic information, and they scale to demonstrate amazing emergent capabilities. So just as a quick recap, how does today's large language model paradigms works? So like here's the architecture, you will be familiar with it. This is a transformer cell. So basically it carries out next token prediction, predict the probability over distributed over a vocabulary, and we train such a model using a large number of corpus curated over different domains. And as we notice that as the data and model scales, they start to demonstrate amazing capabilities, such as they can acquire a large amount of knowledge, they can be post-trained to follow instructions, and they are able to carry out chain of thought reasoning. And most recently, we also found that they are actually able to plan to solve complicated tasks. However, I'm also going to argue that just language modeling alone is not enough for us. So why is it? It is because both the digital world we deal with every day and also the physical world we live in, they are actually filled with information coming from different modalities, like images, audio, video. So if you surf on the internet, like you will get what I'm talking about. And also, like, suppose if we're building AI systems that's going to interact with us real time in the physical world, we have to deal with multimodal information. So the goal is to build basically AI systems that's not only processing symbolic knowledge, but is also able to seamlessly handle these multimodal information thrown to us, like in terms of visual and auditory information. And actually, if you pay attention to today's state-of-the-art language model landscape, you will see, like, for a lot of like recent models being rolled out, they have already been claiming that these models are native multimodal and like are able to process large amount of multimodal information, which is true. We see like very amazing capabilities from these models in terms of image, video understanding, visual agentic coding, and so on. So the first part of this talk is just going to dive into the building philosophies of such models. So what do we call, what do we define as native multimodal language models? I myself personally find it's easier to understand this paradigm by thinking with an analogy of language models. So the state-of-the-art multimodal language model architecture is really performing tokenization across the board, which means whether the incoming information comes as image modality, video modality, or it's a piece of audio, we try to find a way to convert these signals into token information that can be processed by the transformer. And on top of that, we perform a global autoregressive generation modeling similar to language models. So exactly what do I mean? So for text, we can tokenize them similar as what we do for large language models. Usually we can use byte pair encoding, break down the text into small pieces of tokens. And for images, turns out we can also do similar things. So when like a whole piece of image coming in, we can perform an operation which is called petrify. So basically we can divide this image into small parts. And parts is usually predefined like by a standard size, such as 16 pixels times 16 pixels. So once we standardized the image units, we can run, for example, encoders on these image units and get vector representations of them. And then we sequentialize this vectorization of the image units, and then we got the image tokens. For audio, we can perform similar operation. When the waveform comes in, we can perform transforms on top of the waveform, and we can apply certain operations basically to tokenize the resulting representation. And accordingly, you can encode your audio tokens as well. And for videos, so this slide is dense, but like what's really is saying is for videos, we can also easily see them as sequence of images. So if we think of a video segment as a sequence of image, we can perform the similar patrification on each of the video frame, and then we concatenate the patches of all the images in this video sequence, and then we can still represent the video as a sequence of tokens. So when I say tokens, they are not necessarily discrete tokens. They can be, if we encode them into a dense vector, we still refer to them as tokens. And basically, we perform this tokenization across the board, and then like we can basically getting multimodal information sequence, we can train them in the same way as we train a large language model. So for state-of-the-art multimodal language models, when we speak of them, usually there are two broad types of them. So one type of multimodal models consider multimodality as input, but only text modality as output. So as is shown here, so like we have a multimodal sequence coming in. We condition them, but we only calculate the losses on the text tokens. So these can form like, this can induce amazing understanding abilities. Like we have an image as input, a video as input, the model can start answering questions in text. And in fact, like lots of multimodal language models you are probably familiarized today, like Gemini, Qwen, and Kimi, like they operate in this mode. So which means it's multimodal input and text-only output. Of course, like I think these companies have also developed other models which is able to generate multimodal information, but a lot of the core products is doing text-only output. So there is another categories of models which is called the omni models. So which means they not only take multimodal information as input, but they also do multimodal information as output. In this case, like these models is capable of generating not only text, but also images and audios. So something like you might be familiar with like GPT-4o, so like which is named Omni because it can also generate images. So this is an important slide for today because I think this summarizes that by taking this tokenization view, how we could transfer a lot of like the architectural and training principles from the large language modeling paradigm to the multimodal paradigm. So like there are a couple of benefits we can get from it. So first, by designing such architectures, this allows us to build multimodal models, which is able to allow us to conduct prompting and instruction following. So we can prompt these models with mixed modal prompts, and which and enable them to solve like complicated tasks which requires multimodality. These models will also acquire planning and reasoning capabilities, and now even more amazingly is they can plan and reason with multimodal information. So another exciting thing is we also observe that some positive learnings from large language modeling, including scaling data and model size that can lead to performance improvement, can also be transferred to multimodal. So which means like for these models, we see significant promise that if we further scale up the number of parameters in them, and also like we scale up the training database, their performance is going to get better and better, and we're going to see more emergent capabilities. So the only interesting remaining here is, I think unlike text modeling, which has very accurate scaling laws. So basically people is able to derive the power law equation and fit the coefficients of these equation. I think the exact scaling law study for multimodal is underexplored. But on a rough trend, we are still seeing like this scaling capability. So I think overfit, for example, like trying to find the exact fit of multimodal scaling law could be like a very interesting future research topic. The fourth is a lot of like architectural scaling techniques and also like efficient techniques such as mixture of experts and its variations, we can also apply them directly to multimodal language models to achieve like better scaling performance. So next, I basically want to talk about like the second category of multimodal models, which are the omni models. Like because my past research group has been dedicated to developing such models, and I want to present a few variations of these. So when we come to omni models, because they can generate not only text modality, so there are a few key research questions. So the first one is, how do we enable them to generate the non-text modalities? And the second is there possible transfer between understanding and generation of the non-text modalities? So with these questions in mind, the first model I'm going to talk about is the chameleon family. So these models adopt a very simple hypothesis. So basically, the question it asks is, can we actually simply tokenize every modality, converting them into discrete tokens? This is like a very powerful view. If it is successful, it will allow us to model the multimodal world as a sequence of discrete tokens, so that lots of properties of language models could potentially transfer. So this is basically the hypothesis with the chameleon models. And the key here is, how do we discretize images? It turns out it's not that difficult. So like, remember the patchify view we just talked about? So for chameleon, basically we just apply another step of vectorization of this image patches. So how do we do that? Is like, given an image, we converted them into patches, and then like basically we run continuous encoders on top of them to get the embeddings of these patches. And once we get these patches, we don't stop there. We follow it up with a learned vector code book. Then basically we can take our computed embeddings and try to match them with a code book, basically to get the closest discrete correspondence of each of the patches. And by this way, basically, we can convert an image into a sequence of discrete representation. And that's how we tokenize the image, which is really by like finding their corresponding index in the code book. So basically, we discretize the images using the VQAE technique. And then like we put the image and text together as an interleaved sequence. And then basically we apply cross-entropy language model training objective on this. So the result of the chameleon model, basically we found that it is able to generate interleaved text and image in arbitrary order. So like here, like I'm showing like a sequence of image and text generated by this model. So basically you can see like we can actually generate like mixed modal documents from this model directly. And with this representation, it will also allow us to perform multitasking, similar as like how we do with language models. So basically, we can give these models mixed model prompts and get output from it, such as like we can chat with it, do brainstorming, compare images, and so on. So this is a model that purely trying to apply the large language model technique to mixed model modeling. So it is one of the first model to show that like if we train from scratch interleaved text and image sequences, it can induce multimodal capabilities while preserving like the strong text-only performance. However, we also realize some limitations when we discretize the image. So basically, one is like for image understanding tasks, discretization often causes like significant information loss. So as a result, when we compare it to the state-of-the-art multimodal language models nowadays, which is running like continuous image encoding such as SIGLIP, there's usually like a significant performance gap in terms of image understanding. And the second is, even on the generation side, we also found that basically discretizing the images and generate them like actually poses some challenges in terms of like token efficiency. So these models, like, which means these models typically needs to be trained on large amounts of data to be able to sample like well-formed images. So in summary, Chameleon presented a very interesting paradigm where we can train text and images interleaved from scratch. But we also found the limitations. Basically, the assumption that we can discretize information in the images might be too strong. So transfusion is another approach which is proposed in roughly the similar time as Chameleon, so which basically tries to actually overcome some of the limitations of Chameleon. So transfusion is a very interesting and also impactful architecture. So basically, it tries to adopt continuous representation of the images, using them as input, but also tries to directly predict these continuous representation of images. So how do we predict continuous representation of images? So if you are familiar with diffusion models, so basically diffusion models is a very successful approach for image generation. And it conducts image generation by sampling, starting from a noise and continuously predict the noise to be removed from this initial noise until you arrive at a clear picture. So basically what transfusion does is it combines autoregressive language modeling and diffusion-based image generation in a single transformer. So the input to a transfusion model is still an interleaved text and image sequence. And for the text, we perform standard autoregressive modeling. But for the image part, we instead of like doing autoregressive prediction, we take a segment of image representation and basically try to do diffusion operation on it. The model can perform multiple steps of diffusion, get the clear image, and then take the clear image as input and move on autoregressively. So some important architectural changes related is like for text, we can continue to use this causal attention structure. And for the images, for the sake of better performance, we apply bidirectional attention on top of these images. So this is the transfusion architecture. So as shown in the transfusion paper, so these models is able to quickly generate much better image quality compared to discrete token-based image generation using much less token budget. So in summary, so transfusion is a first approach which seamlessly unify autoregressive next token prediction and a diffusion objective for multimodal modeling. It demonstrates significantly better image generation quality and token efficiency. On the other hand, there is also open research problem because for the transfusion paper, it is still trying to represent multimodal information in a text and image interleaved sequences. However, it adopts the VE representation for the images, which is very efficient for generating the images. But on the other hand, these are not very efficient representation for image understanding tasks. So this creates a dilemma. So which is still an open problem, I would say, in the research field today. Basically, the field found that for image generation and understanding, we sometimes need two types of encodings for them. So state-of-the-art omni models today often tries to overcome this shortcoming by adopting two types of image encodings. Cool. So we talk about two types of omni models, using different representation for the image modality. So what else can we further innovate on this architecture to basically make them more efficient? So next, I'm going to talk about a technique which modifies the transformer backbone architecture. So basically, the motivation comes from that. Now we are having the transformers process multimodal information. However, different modalities have different information density. The nature of the data is also very different when it comes to text and images, for example. So the question is it necessary that we have to use a unified transformer parameters to process these modalities, or can we actually introduce something specialized to each modality? So this basically takes us to an architecture which we called mixed-drop transformers. So basically, the idea behind the mixed-drop transformers is we try to come up with an independent set of transformer parameters for each of the modalities. So by independent set of parameters, I'm referring to such as QKV projection matrices in the attention layer, as well as the feed-forward layer. So basically, we have an independent set of parameters for transformer parameters for each of the modality. For the text modality, as shown here, given an input sequence with interleaved modalities, we basically select to activate the set of parameters based on the modality deterministically. If it is a text token, we activate the text set of parameters. If it is an image token, we activate the image parameters. If it's the audio token, we activate the speech parameters. So as shown here, we perform this in the attention layer. Once we get the QKV projections separately, we perform a joint attention over these modality tokens to allow them to unify. Once we get the unified output from the attention layer, we pass them through the feed-forward layer. And the feed-forward layer here, again, is divided by modality. So each modality will have its own feed-forward parameters. And once we pass these tokens through the feed-forward layer, we get the normal transformer output. So basically, from the outside, we still have a transformer unit. We get the token input and output. But on the inside, the processing for each modality happens differently using different set of parameters. And this technique can be combined with the two models I just talked about, with the chameleon models, which is using autoregressive cross-entropy objective for each of the modality tokens, or with the transfusion technique, which is using autoregressive objective for text and diffusion objective for images. So I'm going to show some experiments we conducted with this architecture. So basically, we did a scaling ladder for this one, and we scan them we train them for different model sizes, from the smallest, which is 163 million parameters, to the largest, which is 7 billion parameters. So we always compare them with basically the dense baseline. And notice that if we directly compare it with a dense baseline, basically mixture transformers will have an advantage because it has double the parameters. So we also compared with a baseline which is basically a 4-expert mixture of expert model, so which has roughly the same amount of total parameters as the MOT model. So here are some results. So basically, we show the training loss and also the validation on the image modality generation. So like we show the validation loss, we also show some basically sampling-based image generation evaluation metrics. So one thing we found is that the mixture of the transformer technique is especially effective at improve the generation of non-text modalities. So here, like I didn't show the text modality generation. You can refer to the paper, but like in the paper, we found that actually MOT architecture will demonstrate similar comparable text performance as a dense variation. So what it really shines is it is able to, without sacrificing the text performance, achieving much better performance generating non-text modalities, such as images, as is shown here. So like here you can see like the right curve, basically MOT will have a much lower image generation loss. And also on the sample evaluation, it will show much better performance compared to the dense variation. So, so an explanation for this is non-text modality generation is probably something unique compared to text generation. So if we put everything inside a single transformer, like there might be severe like capacity competition. But if we can allow these separate abilities with different set of parameters, we are able to scale them much better. So like here are some qualitative results. So basically we show that for the top line, which is the dense baseline, and the bottom line is like the mixture of transformer architecture for image generation. So basically we found that across many examples, the MOT architecture is basically able to follow fine-grained instructions much better and generate like much detailed objects. So here is just to mention that the mixture of transformer technique can also be combined with mixture of experts. So what I meant is, so before I was saying like for each of the modality, we keep one copy of the transformer parameters, but we can also use the mixture of expert technique to scale them. So for example, we can choose to allocate different amount of experts to different modalities. So I think we used to find that allocating more experts is especially helpful for text performance, while for like abilities such as image generation, usually it doesn't scale as fast as text when you're adding the number of experts. So which motivates us like we can potentially have customized number of experts for different modalities. Cool. So to summarize, so basically the mixture of transformer technique I talk about, it is a technique which employs modality-specific parameters, and it performs deterministic routing on the tokens when passing them through the transformer. These techniques, we found it to be able to substantially improve generation quality for non-text modalities, including image and speech. And we found that it's also a technique which is helpful to enable the overall stability and controllability of mixed modal training. Because now we have different set of parameters for different modalities, this can actually allow us to perform asynchronous training for these modalities. So a common scenario people use it is if suppose we have some off-the-shelf text models already been built. It has very strong text capabilities, and now we want to add, like, for example, image generation or speech generation to this model. So then instead of performing full fine-tuning or continuous training on this on this existing off-the-shelf language model, what's possible is to add an additional set of parameters for image or speech to it. And then we can freeze the text model, keeping its text capability unchanged, and just training the image and speech parameters. So this is basically allows a simple technique to extend existing models with additional modality generation. Question?
Images and the generation of images are two different systems. For example, the text-to-image is more like large language models, and image-to-text is it's another way around. It's like image-to-text is more like large language models, and text-to-image is more like diffusion models. But it's multimodality, meaning that you want to unify these, like having a single model to achieve the best in both directions. Or is there a loop, like image-to-text to image and things?
Yes. So this is a very good question. So basically, the question asks about so image understanding, which is more image to text, versus image generation, which is more text to images. They seem to be different capabilities. Are we here talking about like having a single transformer which is doing well in terms of both? So this is a great question. Actually, it is not. So here, like when I'm talking, so in the mixture of transformer context, when I talk about image modality, I'm referring to image generation. So I think we actually didn't found like modality separation to help image understanding. So it seems that the capability is bounded by whether you are outputting text or outputting images. But if you're outputting text, your input tokens better go through the same set of parameters, whether they are text or images. Yeah, so that's a great question. Yeah. So and finally, just to mention, since its publication, so MOT has inspired a growing line of following up work in modality-aware architectures. So I'm going to quickly talk a few work done by other people, which inherited the MOT modeling architecture. So the first one I'm going to talk about is actually related to the question just now. So basically, in last year, there was a very strong Omni model came out named Bagel. So Bagel employ architecture very closely related to MOT. So basically, they have separate set of parameters for image generation. But on the other hand, their base model is actually a multimodal language model. So basically, they have a separate set of parameters for image generation. But for the understanding part can actually take in both text and images. So they were so basically Bagel was using a different set of encoding representations for image understanding features. And also image understanding and image generation goes through separate set of parameters. So I think this is also related to a problem I just mentioned before, which is the field haven't yet found a very effective way. So there's currently ongoing research, but I think right now we don't have a very effective way to unify image generation and understanding. So here. One interesting capability shown in the Bagel paper is because recall we are modeling mixed modal sequences as a autoregressive generation. So it unlocks capabilities such as we can allow the model to plan before it generates an image. So basically the model can first generate thinking tracing text and then generate the final image. So this, the paper showed that this would allow the models to generate images with much better details. And I think it's also that this basically thinking before generation is also the technique which is used by lots of the state-of-the-art image generation models nowadays. So another type of adoption for the mixture of transformer architecture was actually in the embodied AI community. So basically, it's very interesting that we found, so it wasn't included in our original paper, but we actually found that in robotics, actually lots of current architectures will use MOT-style architecture to predict the action vectors. So basically, instead of like generating images, so for these type of problems, action is a different modality. And basically, these models will adopt like an actual special set of parameters for action prediction using an architecture very similar to MOT. So again, basically, the idea is while it is having a separate set of architecture, the overall language modeling structure and the self-attention in the transformer will allow the base language models, word knowledge, and so on to transform to the action prediction, which will make the prediction much better. Cool. So yes, so here, like I actually also have like a special set of slides dedicated to the question we just discussed. So basically, is there positive transfer between understanding and generation of the non-text modalities? So here, like I think we need to see them like in two directions. So basically, in terms of whether understanding can help generation, the answer is strongly yes. So basically, people found that if we build better understanding capabilities in the base model, so this will allow the model to have much better like information processing ability, planning ability, reasoning ability. So it will allow us to generate images with much more fine-grained details, and for infographics, it can generate infographics with more accurate information, less hallucination. But on the other hand, suppose like we take an omni model and we further train them for generation capabilities on the non-text modalities. There has been little work showing that this has a positive transfer for understanding capability. So in this, in plain words, which is, if we train the model for image generation and we train it on a lot of token budget, it doesn't necessarily improve the model's ability to perform image understanding tasks. So which is very interesting. So I think related is last year, like so basically the Berkeley professor Sergey Levy also tweeted on his account. Basically, he mentioned that it is puzzling that we basically a language model can acquire such amazing abilities through next token prediction, but on the other hand, we don't make video models much stronger if we do next frame prediction. So this is a very interesting phenomena people have observed. And a couple of explanations, they are a little bit hand-wavy, and which is also like, some of them is also included in Sergey's original post. So one hypothesis is language is fundamentally different from the other modalities because it is a highly compressed abstraction of human cognition. So when we are training on language next token prediction, we are actually already trained on basically humans' reasoning process, and also like some of the words we say also implies actions we are going to take. Versus in comparison, like the images and videos, they are sensory data. They are not our subjective interpretation of the word, but instead they are the passive observation of the word. So like training on them, like will have very different consequences compared if we train on languages. And also for image and videos, the loss landscape is more complicated. So I think so there has been some experiments basically showing that even when like the image and video generation is not looking great to humans, their loss might have already been starting to look good. So basically, like designing like the loss landscape for image and videos are also more complicated. And there's also other hypotheses. For example, like if we just look at the real world, next frame prediction would be very redundant because there will be lots of redundant information and replication across video frames, which could possibly contribute to this. But I think. Overall, this is a very interesting phenomena worth bearing in mind, which could also point to us that although we see lots of success, like applying learnings from large language modeling to multimodal modeling, this is likely not the end. So there is much more fundamental problems to solve when it comes to multimodal models. Yeah. So here is basically a summary slide. So basically, what it says is the models I just presented, like which I call omni-language models, like chameleon, transfusion, mixture of experts. So they solve a small subset of the multimodal intelligence problems we face today. So they especially excel at multimodal information processing. But when it comes to like the wild physical world, when we talk about things like spatial temporal understanding, real-time understanding, robotics control, there are still lots of like unaddressed problems, and people are still dedicated to understanding and coming up with better representations for these multimodal information when you come to real-world processing. With this, like I want to conclude my talk. So basically, I hope like this talk has motivated that building models with native multimodal capabilities is a very active research field nowadays. It has a ton of open problems. It's not as figured out as language models. And for today, lots of like multimodal language models we see, they excel at like digital information processing, but like we still are far away from like a paradigm which could like perform powerful physical world multimodal intelligence. Multimodal models compared with text models, they are more computationally heavy, which requires additional challenges to be solved in terms of training and inference infrastructure. And also, like multimodal itself is a very complicated and interesting problem space. Like we just mentioned, like digital information understanding would require multimodal processing. Physical intelligence would require multimodal processing. Robotics would require multimodal processing. So in the short term, we will likely see an increasing number of multimodal models customized for these certain capabilities, and how to unify them like into a coherent system. That will also be like a very interesting future research paradigm. So with this, I will conclude the talk, and I'm happy to take more questions.
All right, great. We'll be taking questions in person and online. I'll go around with the mic.
Hi, thank you for coming. My question is kind of broad, but more generally, I think there's like certain information that humans are able to interpret visually, and other information that we interpret through words. So I'm wondering, when you're coming up with these architectures or thinking about these models, how do you consider these different streams and how to like actually trade information between them? Because if you do have this mixture of experts, you're sort of isolating how they learn at work.
Okay, so the question is like, so for example, like we just presented a modular architecture like mixture transformers, and if we isolate the representation for different modalities, how do we still like able to unify the information? So one thing is like definitely these models still have the self-attention mechanism. So once like we project like the different tokens using their customized projection, they still go through like self-attention. So that is one way like to allow like information still transfer across modality. So I think that's one thing. And I think the other way it goes like basically modeling still happens is like through this causal conditioning. So we still have this structure of like given input as image, like you need to do text prediction. So even like with separate set of parameters, so these autoregressive order is still there. So that's why like we are still able to model like conditioning on this text, generate this image, conditioning on this image, generate this text. Yeah.
I have a question. What are your thoughts on Japan world models for solving some of the things you discussed, like real-world sort of interaction, multimodal sort of learning, and so forth? Because I know one slide you mentioned how language might be sort of an abstraction of our reasoning or thoughts, whereas pixels, are more dense, but I think with Japa and stuff, they're trying to abstract that as well.
Yeah. So I think Japa is a very interesting architecture. I think I recall. I think at the beginning of this series, we also have a talk on Japa. So how do I see it? Is I think it is because multimodal space is so rich. So we have different types of problems to solve. So we might actually have the need for different representation, school of representations for different applications. So nowadays, I think one thing we observe is if coming to infographic understanding, like understanding PDFs, visual coding. So it seems like our current Apacheify and encoder paradigm works very well. But on the other hand, infographics is also a very different kind of image modality compared to real world, especially scenarios where it requires physical spatial understanding. So I believe Japa is kind of it's an architecture specifically designed to be more efficient in terms of modeling some of these relations. So I do think it's worth basically we should explore different architectures, especially when it comes to this real world physical understanding.
No, thanks for that response. Anybody else have in person?
Hi, I'm curious to get your thoughts on learning more from these multimodal models where maybe there's extra understanding that comes from understanding the world that could transfer to just general knowledge work and agent capabilities. Do you think there is room for that to happen?
Sorry, would you mind to repeat the question?
Yeah. Do you think it's possible that by training these natively multimodal models and omni models, they could get better at general knowledge work, not just at, for example, generating videos, but as humans, I think we learn a lot from the real world. Do you think there is room to make models that can learn from video and other forms of modality that make them better at just knowledge work?
Yeah, okay, so I think the question is if by training these models for video generation, can we make them better at knowledge work? The short answer, as I just touched a little bit in the talk, is so far we haven't found it to be very effective for this type of transfer. So in terms of we do video generation versus transferring back to knowledge work. But on the other hand, I do think we have more promising signals now because I think, for example, lots of robotics task training, it actually requires basically it's being assisted by some video models for future state prediction, get feedback, and so on. So I think there could be a way, but I think so far we are still in a state where we haven't seen that we just train a model purely for video generation, and then it got massively better at agentic task. I think it's really so for example the video generation capability is used as a feedback for how you do the next action prediction.
Any other in-person questions?
Well, I was wondering if you've done any kind of scaling law where you turn actual text into some kind of black or white pictures, because we do know that if you remove those quantization from VAEs, the tokenization the learned tokenization shouldn't be a problem. And in fact, if you have a tiny model that is conditioned on the text and generate just an image of that text, that's also doable. And so it's just that it's not token efficient, it doesn't work well and all that, but is there a scaling law that says it's 20 times worse or something? Consider that, one of the Gemini models can now solve Sudoku in the video, right? So how worse is that? And is there a crossover point where you can kind of achieve that with just decent engineering and then remove an entire modality and just fuse text and image this way?
I see. So basically, like, I think the question is like, is it possible to just render text as images, and that's give us a way to unify the modalities?
Specifically because now the VAE seems to be a bottleneck, and now that we do pixel level predictions and all of that, and it seems like, we're not overly wrongly compressing images anymore because VAE seemed to not have been made with that particular use case in there.
Yeah. So I haven't done such experience myself, but I do remember seeing a paper early on coming out this year. So I think I recall the paper is about basically like kind of like they are training language models, but just giving images as input. And they actually got pretty good results. So basically, like I think then later you can prompt this model like by showing it like OCR images. I think we should all check out that paper, like whether it has like efficiency or like the scaling law study, like so how efficient it is. My prediction is it will be less efficient compared if we train on raw text. I think just because like I think text already have this nice symbolic structure. I think there is a question whether at a large scale, for example, this might go away. I think to me, at least like a very subjective opinion is it's still inefficient. So in the sense that even if we do OCR, like there will be like how you choose like the appearance of the text, like how do you model the paragraph. So there might be certain inefficiency we overlook in this representation. So I think one argument OCR could be faster is I think OCR input would allow us to actually use a shorter context to represent more text, because we can like take a screenshot of a paragraph, like and then like we can just take patches for that paragraph, like versus like, we tokenize the entire paragraph. So I think there is some argument about that. I think it's interesting, and someone probably should do that experiment.
So the reason why I was wondering is because you right now they don't know that, for example, the text is highlight or italic, and you have to add these markdown tags to right. And now they will just naturally understand that. And you mentioned these infographics. It seems like they'll just unify pretty well. And more from an engineering perspective, I was wondering if you fuse these modalities, you'll end up having a much easier time training that, because you only need audio and picture left, and then all the downstream mixture of expert stuff will get easier, and the training will stabilize, probably easier too, less babysitting. So it seems obviously inefficient. But on a larger scale, on a training dynamic scale, it seems like it could be much more efficient because of that.
Yeah, I feel like someone should study this. The only thing is, I feel like at least from what we so far we learned, if we want to unify these modalities during training, it's actually better to align other things onto text versus having text aligned to the others. Because I think text usually drive these like underlining, reasoning, agentic capabilities. If, for example, if we represent text as OCRs, for example, it might just make like scaling to these capabilities much slower.
Oh, how do you make image into the text modality then?
So this is by the tokenization I just mentioned. So like we just divide them into patches.
Oh, that's what I was proposing earlier. Like you turn the text into these kind of image patches token, and then do the regular autoregression on it.
Yes.
Not a diffusion process wholesale, but just auto-regression on the image patches that happen to contain text stuff.
Right. Again, never tried it myself, so it's probably worth. Try some experiments, but I kind of feel like predicting clean symbolic symbols versus like these like imagified text. I think the former might be more efficient. Yeah.
Any other in-person questions? All right, there's some from online. Yeah, someone asked, could it help to develop higher-level, more object-oriented embeddings for visual elements? So infants or humans, we naturally understand pieces moving together as one thing.
Yes, I believe so. Like, I believe this is also kind of the research theme of JAPA as well. So basically having like more semantic representation of the visual things. I definitely think it's a very interesting direction. I think people should explore. Yeah.
I think the other questions are somewhat related as well. One of them is asking, is it feasible for a single representation to capture enough for perception, generation, and reasoning? Or are separate hierarchies likely needed, similar to how humans sort of process or think?
Yep. So I think there has already been research started. Like, I think there are papers published this year, like super apology, I forgot the title of the paper, but it's from Signing Xie's group. I think basically it's investigating, can we unify the representation for image generation and understanding? I think people are seeing promising results. So for example, in the sense that there has already been experimental results showing even if you take standard image encoding representation using that for generation, people are able to generate good images out of it, sometimes even outperform the VAE representation. So I think philosophically, if this direction got figured out, basically that will push image modeling closer to language modeling one step further. Because for language model, we are able to have this kind of unified text input and output. So I feel like philosophically, this path makes sense, and the field is also making progress.
I have a question that's kind of subjective.
Yep.
Do you think we should be trying to make everything like large language models autoregressive? Because I've talked to some folks, including Andre, and we have mixed feelings about next token prediction. From a sort of cognitive standpoint, or at least the way I think about it, I feel like humans learn in more structured hierarchical manners, not simply predicting the next token given all the previous ones. That's more of a statistical learning procedure, which works well with LLMs because you have so much data. So you're able to estimate this sort of distribution effectively. But I feel like fundamentally, this is controversial, but I feel like autoregression is flawed, or it works well. It works surprisingly and impressively well, but I feel like we need something more. I feel like just next token prediction might not be the move, but I'm not sure if you have any thoughts.
Yeah. So I think the thought is very interesting. So I think there are people trying different things like diffusion language models, right? Discrete diffusion language models, different ways compared to next token prediction. I personally think next token prediction has proven itself to be very effective. And I think the catch is even on the surface, it's doing next token prediction because the network connection is pretty complicated. So there could already be structure learning emerged in the latent space, which I think, which we don't understand well, but it could be that next token prediction is the surface form. The network is doing more than that.
I know, I think that makes a lot of sense, yeah. I feel like because of how the transformer and attention works, I think you're right, that there's a lot of abstractions or sort of structure that's being learned that's sort of hidden. And sort of next token prediction, like you said, might be the sort of surface way that's at least it appears like that's the way, well, that's the way it learns, like the training objective. But it's actually learning more than that. Yeah. Any other questions or?
Thanks for the presentation. So what is your take on the state of the art when it comes to spatial reasoning? So kind of physical environments and modality, multimodal models.
Yeah. So I'm not an expert in the area of spatial reasoning. So I think in terms of the state of the art, so I think we're seeing lots of progress in robotics. In robotics labs, these vision, language, action models. So I think one interesting observation is I think some of these actually they're being accelerated by like multimodal language models. So like for example, like even for the models coming out from like physical intelligence, like they leverage like vision language models as a backbone rather than training from scratch. So it seems like there are some interesting positive transfer from multimodal language modeling to spatial understanding. So I think on the other hand, there are definitely more labs like which is taking more unique approach. So, but I'm less familiar with those approaches. But I think like I'm aware of some approaches which is like shifted more further away from leveraging languages, like but like kind of like having the model more like less language dependent, but like focus more on the vision signal. But I'm not too familiar with those approaches. Yeah.
Sorry, I have one more question. It's regarding what you said about reasoning being done much more effectively in text space rather than video space. And how much of it is a video data problem rather than pure problem of visual video? Because there's no good video data where the person pauses a bit and then he monologues a bit, and then you hear the sound of it or something like that. Whereas in text, it's like most texts are full of reasoning and monologue and pauses and all these kind of stuff. So if you, in theory, if you train a video model and intersperse it with frames of like text or something like that, then this reasoning problem seems to be solved, like you said, and it would be either audio, which is a approximation of the text, or the text itself. So I guess what I'm trying to ask is, in what part of this don't we already have a proof that when you want reasoning, you have to go down to text anyway?
Right. Okay. So, okay. I think the question, to repeat the question is
It seems like you can only synthetically augment video through text,
right.
Through text in the video or text in the, I don't know, the MP4 frame or text into audio into that channel.
Right.
It seems like that's the only thing we can do. And if so, that's much stronger proof that we have to do synthetic data with video interspersed with text in various format. And then nothing else will work as well.
Okay. So I think basically this assumption is building on like we have to reason with language as a backbone. So I think that has been shown to be very effective, and I agree. Actually, synthetic data is nowadays very important for vision tasks. So it's always very important. But I think that doesn't rule out the possibilities that we can still have pure vision models that can reason. So suppose nowadays if we have like very good let's say like video next frame prediction, and like we just prompt it with just what's happening in the video. If it is able to like get like next like what's happening in the future accurately, I would call that a type of reasoning.
Right, but the data would be lacking for lots of these kind of video reasoning stuff because it's hard to generate that as opposed to text, right? And the other thing is it's the same question kind of where in a textual chat app, you can just slice out text, and for example, you can slice out the reasoning and everything's fine. Whereas for video generation, we actually give it to the user as it is. For various reasons, and we don't ever get to pause and do some video special dedicated video reasoning frames that we strip away with a post-processing pass to the user, and so it has to be, every frame has to just mean something. It's like you don't get to do reasoning at all in the video space purely as a UX concern because it's already slow enough to generate, I guess. So.
Yes, I think efficiency wise, that's true.
Okay.
So I think I would agree. So like nowadays, if we use language as a skeleton, it will help visual reasoning much more. So I think that part I agree. But I think that's also partly because language compared to vision information is much more abstract. I think if you can have but I think in some sense like nowadays we train the model to go back and forth, like from like visual signal into like this abstract space, like because we train it on captioning and other things. I think this has proven to be useful. At least it's useful nowadays. I think it could be an open question whether that's like what we maybe at some point when like compute skilled good enough, we can do like just reasoning, like just in like pure visual space. Yeah.
Awesome. Thanks again, Victoria, for the amazing talk. Let's give another round of applause.